Okay. Hello. Well, welcome back to week 2. It's nice to see everyone again. Hope the start of the quarter is not too bad. Mine's getting a bit better now. Somehow week 1 was worse. But there's the attendance form. Go ahead and do that. On the topic of attendance, skiing won from the last week's like more than 2-1, which I like. I'm a skier, so that's cool. Who all went to, raise your hand if you went to California over spring break. Yeah, there's a decent amount of people that I did too. It's kind of cool. I don't know, I was looking through that and I was like, what are the chances? Some notes about the project. Again, the future week stuff will be due next week. And when we say due, it's a very strong suggestion. Maybe in the middle of the quarter, we'll actually like not accept any afterwards. But if you're running behind, which I know I am too in my classes, just let your TAs know, and they should be able to like give you more time. But do let us know. Don't just like, we don't want to see every single project and synthesis questions on like the last week. Yeah. Just that'd be rough on your TAs. Any questions about the first week? Things about that? Cool. Today is going to be Unit 2. Varun will be doing a lecture. Again, if you missed the attendance form, it's in this chat, it's in the resources chat, the turtle emoji in the Discord. And we didn't get many submissions this week, so tell your TAs, get extensions, and do it. If you do it, we'll reward your efforts. But yeah, I won't waste more time. We can go straight to this.
All right, should I just start?
Yeah.
All right, awesome. Okay, hey everyone, I'm Varun. You may have seen me at the beginning, right? Yeah, you guys saw me at the beginning. But today, I'll be lecturing on an intro to deep learning and neural networks. So y'all did the machine learning stuff last week, so that gives you hopefully like a little bit of a basis, like maybe you came in not really knowing what machine learning was, but now you kind of have an idea. This is going to be a new topic, deep learning. And I'll start off immediately by, actually, let me go here first. So just to put this in context so you guys can understand, when we say like AI, it's a very, very like nebulous kind of like bubble of things, right? There's a little like alignment chart of AI, like determining like how algorithm purists, and I don't know if you guys have seen that, but in like usefulness purists, and like people disagree on like whether something is intelligent or not, right? Some people say it has to like exceed human capability for it to be called like AI. Some people say it just literally has to learn from data. It's a jury's still out on that. So machine learning is a subset of that I find to be like very statistical. It has a lot of guarantees. You may have seen that. It's like provable that you can actually find a solution to this stuff. You may have seen like the simple linear regression equation. You just transpose the matrix, multiply it by itself, invert it, blah, 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 and you all of a sudden you have like a set of weights that can actually get you to like the lowest point possible on the loss landscape, which is really cool. Deep learning is like a subset of machine learning that essentially, well, it's like a trade-off. It's more computationally intensive. I'm sure you've heard about like GPUs and like compute and stuff like that. There's increased power. You can do more cool things with it, and I don't even have to say, like, we all know like what the coolest new recent thing is, right? So there's fewer theoretical guarantees though. So we'll go over some of them. But essentially, you don't have like the nice, clean, yep, we know we got the right answer here. There will be some stochasticity, some uncertainty that's like very hard to remove. Empirical decisions, deep learning, as you might be a computer scientist and come from a background where it's like, I need some closed form solution to this algorithm, blah, blah, blah. And literally, even in like the very, very seminal, important papers of the field, sometimes those decisions are literally like, yeah, it worked. So it's empirical, right? Which might be exciting and also like worrying because it's like, how do we know if we're doing things right? I'll get into that later. And they're also very data hungry. So that's just like kind of just to like set the scene of like where I'm going with this. It's like more power, less like knowledge about it. Like we don't really know what's going on essentially. So I think that's pretty interesting. Backtracking a little bit, I just went over like what is deep learning in general. And the main thing we'll be focusing on is the neural network, which is kind of like the basis for deep learning. It's like one of the first things that kind of like propelled this into importance. And we're going to go over it on a conceptual level. Let's talk about like what is this, because you might hear feed-forward neural network, artificial neural network, multilayer perceptron. Maybe you hear these words or you read them in research papers like, oh, then put it through like a multilayer perceptron. Like, what are those things exactly? We'll go over that so you have the vocabulary to understand these things. And then we'll get a little more granular with it, with the forward propagation and back propagation, which is how these models make predictions and also how they learn. So it's like forward and backward passes. And I'll tie this a little bit to inspiration for neuroscience, and then end with like once you understand a little more about deep learning, I'll do like a comparison DL versus ML. So it's a lot, but I talk fast, so I think it'll be okay. Starting with neural networks. This is the image that I'm going to like be referencing a lot throughout this presentation. So just take a second to like digest this. I know it's like a mess. It looks like a web of things, but has anyone like seen a figure like this before? Like raise your hand if you've seen something like this in like a textbook maybe, or like it's just thrown there as like a figure, perhaps, right? So this is what we're going to be doing. So like next time you see that figure, you'll know generally like what's actually happening, right? Beyond just like this tangle. And more on why it's actually called a neural network later, because like you might look at this and be like, that looks more like a spider web or something, right? So we are going to go, let me just go to the head here. There's some like basic like anatomy of this thing that I want to cover just so I can like use it without needing to worry if you guys understand it later. So first thing is these like rows of dots, they're called layers. Okay, so if I say the word layer, it's referencing one of these rows of dots. And what each of these are, that'll be explained later. But when I say layer, just know like in this schema, I'm referring to like these things right here, right? And more specifically, there's an input and output layer. I think that's pretty intuitive. This is like the start of the network. That's the end of the network, input, output. And anything in between is called a hidden layer. So just if I start using these terms, maybe you're a little confused, please tell me to pause and then I'll like reference back to this or something. So far, so good? Everyone getting that? Okay, cool. Great. And then the other two small things I'll go over, and you'll understand these for sure by the end. One of the dots in a layer is called a neuron, like neural network, right? And then you have weight, which is one of these lines, okay? So is there any confusion on like the anatomy of this thing? Okay, great. So here's a conceptual definition of a neural network and also like why they're so powerful. There is a theorem or like a thought experiment called the universal approximation theorem. It's not the most it's not the most useful thing in the world, honestly, if you look at the argument deeply. But what it says in essence is like with a sufficiently large neural network, you can approximate any function, and that holds universally. Neural networks can approximate any function because they do non-linear transformations. If you understand what that means, great. If you don't worry about it. But just know that if you have essentially some underlying distribution, in this one it's normal, right, with some parameters mu and sigma, and you take a bunch of data from it, this neural network will basically be able to figure out what those parameters are, to estimate those parameters. But obviously, this is something that you can do with maximum likelihood estimation or a more statistically sound method. So I wouldn't suggest using a neural network for this, right? So, but the idea is there. You have a bunch of samples and points, and you want to throw this neural network at it and see what is the underlying function. And why that's useful is that you can now test it on new data and get insights about those, right? So does everyone understand what I mean by it's a function approximator? Approximator is a very important word there, right? I'm not saying it'll suddenly turn into a mathematical function. It is a function technically, but it's not going to turn into the underlying one, right? So it's a function approximator. Y'all got that? Right, great. Please stop me if I say something just way out of whack. I don't know. So that is something that problem up there is something that you wouldn't really use a neural network for, but this is, right? You have this cat. You know it's a cat. I know it's a cat. But how would a computer know, right? That what is the function? What's function of cat? What is that, right? That computes based on this image, understanding it and digesting it and spitting out a confidence score for cat or dog. That doesn't really make sense in our heads, right? What what kind of function takes in an image and spits out confidence and is so complex that it can separate between like these ideas of like dogs and cats in different settings and stuff like that. But it's a function. It's taking an image and spitting out some numbers. So, and that's why neural networks are really powerful pattern recognizers. So yeah, you think a little abstractly when I say it's a function approximator. Don't literally think of like a mathematical function parabola or something like that. It's an idea like of taking images and trying to get some like insight out of them. And there's some underlying function of like what is a cat, what is a dog, and you can approximate that. So before deep learning, you would take the cat, and this ties back into the machine learning unit last week where you basically saw hand-designed features like, what is it, wooden legs, right? Does it have wooden legs? Does it have like hair?
Yeah, does it have legs and teeth? I forgot.
Yeah. So essentially, hand-extracted features, right? Like you can say like number of legs, height in centimeters. I don't know. Height in feet. Yeah, the thing's tiny. Like cuteness out of 0 to 1. It's like obviously it's cute. So like just things like that, right? What defines a cat? Hand extracted. You know, a human has to look at it and like figure this stuff out. And then you feed it into some kind of classifier, right? And if you did your feature extraction properly, this classifier, like an SVM, will ultimately tell you, okay, I think based on these features you gave me, that this picture is a cat. That make sense? So deep learning, you don't have to do all that. You basically, I know it looks a little weird, but you just take the cat, take its just the values of it, right? Like every single pixel that comprises that image, throw them into a long list, a very long list, right? Put that into this neural network, and then what you'll get at the end is the same stuff that we were looking for before, without having to do feature extraction, which, you know, takes a human out of the process entirely, which is great because now we can like learn more arbitrary and interesting things, and we don't need everyone to like annotate and select the features of cats and dogs and so on and so forth. So they learn features that are important. Does everyone understand what I mean by saying they kind of like learn features in the context of this slide and the previous slide? Anyone have any questions? I want a question.
Can you explain what you mean by learn?
Yeah, for sure. So essentially, somewhere in this, and this is going to be kind of abstract, you'll get a more satisfying answer at the end. But when I say it learns this, it means that if you show it enough cats, for example, right, it'll start to get an idea of what defines a cat. For example, maybe, you know, cats always have like fuzz around them, or they have a sharper nose, for example, right? It'll somehow learn that in here in a way that we actually can't understand. But it's clear because of its classification power that it not really understands the difference between a cat and a dog, but is able to like differentiate between them by some extraction of features. So it learns what to look for in an image to classify it properly, right? And in machine learning, to do that, you usually get hand-designed features because we know what to look for, and then those characteristics define a cat. And then you can do some linear separation pretty easily. So forward propagation is the forward pass of the network. It's basically this thing, right? So everyone with me so far? So passing data through the network. Remember what at the beginning when I was talking about input layer, hidden layers, output layers. We are going to put the data into this input layer. I feel like that's relatively intuitive. So you're going to put the data into the input layer, and then through the process I'm about to describe, it gets passed through the network, and then by the time it comes to the other side, you should have that 99%, 1% classification score. You should be able to tell, like, essentially this, by reading this output layer, you should immediately be able to tell, like, what you gave to the network. So then, you know, the cats, dogs, birds, trees, I don't know, that's like the 4 classes over here. Like, you put a picture of a cat, this value should be very high and these should be low. That means cat. You give it a picture of a tree, everything's 0 except for like this one. That's like a very high value. That means that the network kind of like is lighting up and saying tree or cat. That's what I think it is, right? Does that make sense so far? Like, don't worry about like how it gets through it, but like kind of like the ends of it so far. I'm going to go into like the weeds in a little bit. So far, so good? Be honest, because like no questions can be a good thing or a bad thing. I don't know which one it is right now. So, yeah. So, Well, in interpretable and explainable AI research, we're trying to get them to not be black box. So the idea is like, how can we interpret these weights? So you might know what that means. So how can we interpret these weights to actually see what the model is learning? That turns out to be kind of difficult. If you want to talk to me after, there's like some methods like saliency maps, for example. If you may have heard of those. No, okay, it's really cool. Yeah. Okay, no. I'll tell you about them. I think it's really cool. But there are ways, but plain, you can't really do it. You can't just look at it and do it. No. So I'm going to explain how the data goes from this first one to the second one. Literally, how does it just, data, we're going to go from this to this, right? How do we pass it through one layer of the network? And then as you can see, it can go through here and go through here. So I'm going to explain the process that takes data from this to this layer, and then you can extend that to the other layers, right? So we have to zoom in first, though, onto this like tangle. And can someone tell me what they were called when I did like the anatomy of the neural network? Great. Okay. Wow. Thanks, guys. Okay. So they're weights. What do they look like? Well, actually, they look like this. They look like a little like grid. It's stored in a matrix. These lines and such. 5 by 4. Can someone tell me what the connection of 5 and 4 are to this neural network? Like, why are the numbers 5 and 4 important? Why is it not like 7 and 10?
Because the input has 4 neurons,
Yeah.
and then the hidden layer has 5.
Yeah, exactly. And you may not be familiar with matrix multiplication and stuff like that. Don't worry, I'm going to walk through it pretty intuitively, hopefully. But the idea is this weight matrix is kind of like dependent on the number of neurons from and to. And you can see it's like from 4 to 5, right? And that's like 5 rows and 4 columns. And why is that important, right? So our data comes in the form of this. It just looks like 4 things, right? This is a toy example, by the way. In real life, maybe this would be like super, super long, like it would be all the pixels of the cat. But in this case, I'm just going to stick with 4 because I can't fit that all on the screen. So this is what we have right now, a 4 by 1. And then what we're trying to get is a 5 by 1 vector, because that means that we're here now, right? So we're trying to transform this into that using this. Can someone kind of tell me, like, maybe if they know like how that would be done? And go from 4 to 5 using a matrix of 5 by 4. Someone want to give it like their best shot. You don't have to explain like it thoroughly, but like, do you see how something can be done with like the shapes?
You find a cross.
In this case, I don't know if it's a cross product in this case. Nah, it's dot, right? Yeah. So in what we'll do, yeah. So you basically multiply this matrix by that vector. So that's good intuition though. Like there's some kind of combination of these two, right? Here's how it works. Someone kind of like, I wish I could do animations, but like, you see that? You kind of like put the 4 onto the top 4 right there, right? Just kind of like that. This is how matrix multiplication works. You will take the number that's in this box and the number that's in the green box behind it and multiply them together, right? And do it for each one, like 1, 2, 3, 4. So you have like 4 products. And then you sum those all up. And that becomes one number right here. Can someone see what happens if we do this 4 more times? How many output numbers will we get? Great, yeah, 5. And then where are we at? Because here we go, here we go, here we go, here we go. Again, run through that. You guys kind of see that? Oh. So it's like we go from here and we do a multiplication like this, create 5 numbers, and then boom. We are where we need to be. We have created that like 5 by 1 matrix, right? And this is probably where I might lose some people, so I'm going to take this a little slowly. But after we have those numbers, right, which are created just by doing the multiplications, additions, and spitting it out, right, and we just stack them like a vector, you need to apply like a special function to it. Why? I'll explain later because it's hard to explain this first and then talk about the calculus later. But just know that the last step we have to do is just apply a function to it, a special nonlinear function, a very originally common. Now we know it's like not the best one is sigmoid, but you can think of it like, okay, we're just gonna take this function and literally just like take whatever's in here, plug it into the x there, and put that back. It's literally just element-wise application of this function. Does that make sense? Does it actually make sense? Okay, hopefully. Let's see. So that's like one layer, right? Oh, wait, let me go back. That would be, just going back to here, what we just did was from here to here, so a 4 to 5 thing. And we use this matrix of weights. Now you can kind of see there's basically for each object in this photo, there's like a small like number attached to it, right? For every single line, every single one of these lines corresponds to one of these boxes, right? And you can kind of see because you have 4 items and each one has 5 outgoing edges. 4 times 5 is 20 and there's 20 items in this. So that's the connection right there. And the reason we do it like this and not like iteratively is because matrix calculations are a lot faster and they can be done in parallel, unlike something iterative. So that's why GPUs are important, because they're originally designed for other things, like it was for graphics processing, which is a lot of like vector stuff as well. And then now, because this also uses vectors and matrices, we can repurpose them essentially. So there's that. So we're here right now. Can someone on a high level, actually, you know what, let's do this. So there's some chatter. Turn and talk to your neighbor and explain on a very high level how data flows from the input layer to the first hidden layer. Go talk. We have just basically shown how data can flow from the input layer to the first hidden layer. So why is like this transformation necessary? Well, it has some kind of connection to neuroscience in a very loose way, but essentially, the way that neurons fire is nonlinear. Is nonlinear essentially. So you have spikes that will look something like, you'll start here, like this. So it's like this is a spike. That basically means the neuron fired. There's like, I can't get into it too much because then I won't have time, but there is something called membrane potential, and if you put enough neurochemicals into one head of the neuron, it'll suddenly start building up, and at some point it'll fire and basically propagate that signal to the next neuron, right? So it goes like neurochemicals enter the neuron, slowly increase the membrane potential until some pretty cool biophysics happens, and then electricity shoots down the axon, which is that part right there. And then there are axon terminals which connect to other neurons, but the electricity doesn't just go straight through. The electricity actually like then tells that same neuron to then release more neurochemicals, and those activate the next one. It's really interesting how fast that can happen. But the fact that the firing isn't just one straight line, it's more like it builds up. And then it happens, like spikes are like this is the information flow, and it happens only after like a certain threshold. So like right here in time, some threshold was crossed in the amount of neurochemicals, right? And so you can kind of see that like here's like a threshold, right? So like if you don't pass like 0, you're not going to get anything. But once you're there, you've already you fire essentially, right? So after you hit around here, you fire, and there's like something in the middle, so it's not like just a block function, and there's like some smoothness to it because it needs to be differentiable. But that's an example of like why that sigmoid function exists, and a cool neuroscience connection. So we just saw that, and I'll quickly just very simply show how that can be extended. Just do that. Just do the same thing again, right? Except you'll have a different size of the weight matrix. So can someone tell me what the dimensions of the weight matrix will be between these two hidden layers? it would be 5 by 5. So yeah, no, they're really good. So like the weight matrix is like the box. So that one for this it was 5 by 4, and this one the same. So it's like 5 by 5, right? 5 to 5. And if this makes no sense, tune back in after I'm done talking, because don't just like tune out completely after this. But I think this is important to cover. At the very end, you will get something called logits, raw logits. It's just numbers that essentially don't mean anything, right? But they mean something relative to one another. Like one neural network could output like something like 0.5, 0.912. Like, how would you interpret this? Like, maybe, oh yeah, this is the highest number, that means something, right? But like, what is, like this, it clearly isn't like probability, right? It doesn't sum to 1. But you could turn it essentially into a probability distribution with something called a softmax function. You just apply that on the vector, right? And what it essentially does, it will take raw logits and then convert them into something like 0.1, 0.2, 0.4, oh, that doesn't make sense. 0.2 again, and then 0.5. So like the high number here translates to like the highest number here, but now that sums to 1. So you can interpret it like probabilities, right? So, and this is kind of like a visual description of that. Makes sense? Any confusion on that? I learned this like a week ago. Shit, man. Okay. I know there's a version called Hardmax, and I'm sure if you compared the two, you could see why it's called Softmax. I mean, as you can see, it kind of smoothed things out. But that's like my semi-educated guess. But if you look it up, I'm sure Wikipedia has you. So, okay, now this is probably where we're going to up the level of like complexity a little bit and talk about nonlinearity. So, tune in, take a sip of your Red Bull. I don't know. I guess it's pretty late, huh? Yeah. So, can someone tell me how to draw a line, one single line through this that separates the red and the blue? If you can do it, let me know, because I need to talk to you. But like, the short answer is you can't, right? This is a collection of points in space that cannot be separated by one line, right? A lot of the machine learning methods that we use are something like linear. Basically, ultimately you can abstract them enough so that it's basically drawing a line through like a space of vectors and then separating two things, right? Like binary classification. But if the points are arranged in such a way that like you can't separate them with one line, you're always going to have error. Like you can draw a line like here maybe, right? But then like some of the red points will be misclassified, some of the blue will be misclassified. It's like hard. Like you can't do it with just one line. But with nonlinear transformations, softmax is not a line, softmax is nonlinear, right? With nonlinear transformations, you can turn this into a linearly separable problem. And that's why neural networks are powerful, because they do multiple nonlinear transformations. Remember at the beginning when I talked about the universal approximation theorem, the important thing about that is that there must be at least one nonlinear transformation in the network for the theorem to hold, right? Basically, it's like you can't just draw a line through everything and have it work. But if you allow for a network to transform things nonlinearly, you can take anything and turn it into like something that's linearly separable. That's the idea, right? And that's why it's so powerful. And that's also why there's no guarantees, or like very few guarantees. That's why it's kind of problematic. Like we trade off like interpretability for power, right? Okay. Any questions on this? Yeah.
So last week when we were looking at the hyperplanes, I was looking on Wikipedia and there's these things called nonlinear kernels, which are like basically a nonlinear way to to do the hyperplane.
Mhm.
I was wondering, like, why do we like choose to transform it into linear rather than like using a non-linear line? A line is linear, but you know, like a
Yeah. So with the what you're describing is something called the kernel trick, and it's really cool because another way to solve this problem is basically like add a new axis and pull the red points out, and then draw a line this way to chop them in half. Does that make sense? Yeah. That's basically what the kernel trick does, right? Yes, you can solve problems like that. That's why RBF kernel and SVMs, you'll see those two words very commonly together. Don't worry about what RBF kernel is, but like you put them together and it can do more powerful things than a standard SVM, right? However, if you think back to like at the very beginning when I talked about like why neural networks are powerful is because they learn the features themselves. It's kind of like this may or may not be happening in the network. We won't tell, but like kind of like, do we care if the output actually it works, right? We get outputs that are reasonable and useful without needing to like mess with it or design things by hand, right? So answer is you can use like nonlinear transformations like kernels to make like SVMs work for something like this, but notice how it's not really transforming, it's like transforming the data, but you're still drawing like a line essentially. And by pulling it out onto a new axis, it's kind of like a hack. This can do like actual transformations of data through those matrix multiplications to slowly like massage it into the format you want, which is pretty cool. And if that was like somewhat hard to follow, don't worry because I'll touch on it at the end again. So here's some more activation functions. Sigmoid sucks, actually, it really does. Even though it had like basis in neuroscience and all, unfortunately, right? Mainly because its derivative kills gradients. If you know what that means, great. If you don't, you'll know what it means by the end of this. But basically, this is the one that's standard now. You're going to be making a neural network as part of like the unit 2 assignment, and ReLU is rectified linear unit. It's literally just max of 0 and x. Like if it's below 0, don't consider it. If it's after 1, just it's itself. Simple as that. And there's like other fancier versions. Pretty sure the GPT-3 uses like a modified version of ELU called GLU or something like that. But like the Lu family or whatever, like the LiQReLU, like ELU, they're like really useful. We kind of moved away from sigmoid. We don't really talk about them anymore. So, okay. Who is excited to learn about backpropagation? No, like yelling, screaming. Okay, yelling. So this is like the cool part. I think really, really interesting. It does involve a little bit of math. So if you don't follow it fully, I'll try and give the intuition. Please immediately raise your hand if I say something that is a little confusing. No, there are no such things as silly questions. Like actually, so ask whatever you want. This is the basis of how neural networks work. So if you understand how they work forward, this is like, you might think it's magic, right? How do we make the weights in such a way that it perfectly classifies a cat, right? Well, this is how. And by the end, you'll kind of wonder even more how it works because it seems pretty simple. So the general idea is like you have a bunch of matrices, right? Like here's the first one we worked with. Here is a 5x5 for that second transformation between hidden layers, and then here's the last one, right? So these are literally the parameters of the model. You can reduce the model to these matrices, like this many terms, and there's a little more with a bias term, but you don't need to worry about that too much. This is the most of the parameters of the model right here, just in matrices. And if you pick the right numbers in here, you can get something that literally could separate like a dog from a cat, which is kind of crazy, right? But how do we do that? Like there's already like an infinite like search space for each one of these boxes. How do you pick the right one, right? And you can't brute force this. So you have to tune it in like a smart way. Like how do we pick the numbers for this? So let's start by randomly initializing. And there are smarter ways to initialize, but just you can consider it random. We just put random numbers in reasonable bounds, maybe between -1 and 1 into all of these like little squares, right? And the idea is through a little bit of calculus, we can slowly push those in the direction that will give us the best results, okay? So the first thing I'm going to talk about is kind of on the like posterior. No. It's at the other end of like the neural network. Like after you pass it through everything, like how do you know if the model did like good or bad, right? Because you might see like 50% cat, 50% dog. You want a way to quantify that that's a shitty prediction, right? So here's how we do it. You take the output from an untrained network, which you can see here. This means like nothing, right? We're supposed to be cat. Like this is like the cat node. That should be 1. All of these should be 0. But because we randomly initialized, we're basically doing random transformations. We're not going to get that, right? But we know what we want to get because we have a label for the cat, right? So that, because we applied the softmax function to it, remember it turns like a vector into a probability distribution. That's the probability of cat, and we want that to be 1 instead of 0.2. So we take what we got, we subtract what we want, we square it, and we sum it. That's loss. That's MSE loss, mean squared error. And it's really as simple as this. It's just like you have a ground truth label and you have what the model gave you, and you're able to quantify how poor its prediction was, right? Usually higher losses tend to be bad because that means that you performed poorly. So like you can think if this was like, can someone tell me like what the loss would be if this was 1 and the rest was 0?
0.
Great, yeah. So we have a loss of 0, but we don't have a loss of 0, meaning there's room to improve, right? So it's a metric that tells you like how things are doing, right? And what we want is the loss to do something like this, basically. The loss is going to start high, and through time we're going to reduce it until it's like somewhat stable, and we can say we have trained the network, right? Because this is pretty close to 0, so it's getting a lot of things right. Here, I don't think I need to say this again, but basically, yeah, this is a formalization of that. Now, here's a little bit of intuition before we go into the math. You can think of like, we have like so many parameters, right? Each one of those numbers inside those matrices, you can consider each one of those like an axis in some like 50-dimensional space, which is impossible to think about. But the idea is essentially like somewhere in that 50-dimensional space, in other words, a certain configuration of those numbers will get you a low loss. That's the idea. This is a very simple interpretation because again, it's 2 dimensions. We're operating in like 50 or so, right? Or like in the case of other neural networks, like billions, right? So it's a billion dimension space. That's insane, right? But somewhere in that space, or if it helps you think of it better, a certain configuration of numbers will get you a low loss, right? And that's what we want to go for. And essentially, like we can, by randomly initializing, what we do is just pick a random point on this plane, right? I'm going to stick with the 3D example for now. But randomly initializing literally means like let's say that A there, it's a random initialization of the weights. You'll notice how, like, if we want to get better, we kind of want to go down this landscape and we'll get to the bottom of that pit. Keep in mind there's a lower pit there. How do we get there? We'll see. But you'll notice like we want to go down the lost landscape. When I say lost landscape, it's just kind of like the abstract idea of the fact that there are better points, better configurations numbers than others. And it's just something that people in deep learning talk about. Did that make sense? No, kind of. Is there any questions people have on like this concept? Like, how do we want to move through the lost landscape? No. Yes.
How would you move up that A to the global?
Oh, to the global minima?
Yeah.
I'll get to that at the end, but
So for now we're just like moving it to the local.
Yeah, to local minima right here. So that's what we're going to do through backpropagation. We're going to take steps in this lost landscape so that we can like slide down the slope and get to the bottom. And a lower loss means we're doing better, right? So we have adjusted the parameters of the network so that we can classify more things correctly. That's really the high level thing you need to take away. There is a concept in calculus called the gradient. Essentially what it is you have a function, right? It's useful to think about this. It starts becoming useful in like more than like 2 dimensions. Like here's a function of x and y, right? So you have x, y, and an output z. here's a function, and you can kind of see like there are certain directions in which like there is a steepest ascent. Like if you were to kind of be around here, like inside that little like I don't know what the shape, a bullet type thing. If you were to like step sideways, kind of like going around the ring, that's not much ascending you're doing, right? But if you try to go up this wall, that's the direction of steepest ascent. Okay, basically it's like literally just what direction do you have to step in this function? Like move, like think of a dot moving around here, so that it just has the highest like ascent possible. Like we want to move as much as possible in that direction. So like the gradient is going to be a vector, and it's a vector that tells you in each direction how much to move by, so that you can get like the maximal like increase in whatever this is, right? Did that make sense? No, be honest with me, guys. Don't break my heart. Just tell me, like, is there anything confusing about this? Oh, sorry. Yeah, so that's what I'm going to go into next, but I can explain like just in English for now. The gradient is essentially a vector of you take each parameter of the function, and you take the derivative of the function with respect to like the partial of that variable. So like we take the derivative of this function partial like x derivative. How do I say this in a more concise way? Take the partial derivative with respect to x of the function, right? And then you'll get a number for that, right? And then that'll be the first element in your vector. And then you take the partial derivative with respect to y, and you get another number, and you put that as a second element. Those are directions in which to move. Yeah, that's how it works. And then I'll go into like how we can do that in a neural network in a second. Any other questions?
Yeah, I think the minimal is the slope is 0. So why would we going to find the larger slope?
Yes. Sorry, I didn't mean to cut you off, but like that's a really good question. Thank you for reminding me. If we have the direction of steepest ascent, we can negate it and go in the direction of steepest descent.
Oh, okay.
Yeah. So we're not going to start at 0. We're going to like take the gradient, flip it, and move that way. So we can go down the fastest we can possibly. Skip that. So, yeah.
I just want to maybe you're going to get to it. But I just want to make sure that everybody, can you go back?
Yeah.
That everybody understands what our function is representing in this case. Can somebody tell me what our function is representing and what our variables might be?
Is it the x and y coordinates?
Okay, yes. But in the context of machine learning, that would be, what would be the weights? Mm-hmm. And then our function is representing as a whole.
You're really close. No wait. You want to try it again? Like what does this function represent? No. Please.
Something related to laws. We're like trying to optimize a loss to be minimal using. I don't know.
Yes, no, you're on the right track,
Yeah.
dude. So we have the weights being represented by our x and y here, and
Sorry, yeah. And the weights are the x and y. The function is the neural network itself. Remember how I said neural networks are function approximators? This is where it comes in handy to understand that, right? Yeah.
So the loss is going to be a function separate from this. And what the gradient is telling us is not, it doesn't tell us anything about our loss. It just tells us what is affecting the output of our model the most. So using that information, we can figure out how to minimize the loss later.
And I think hopefully this next example should explain that. But yes, that's 100% correct. If you think about the neural network in this context, you can even just like think about it like this for now, and maybe all will come clear at the end. Anything else before I move on? Okay. So not that one. Backpropagation. The last slide was the one I did like last quarter, and I think that's when like I lost people, so I'm doing a more longer but hopefully more thorough example. Here is a really, 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 really simple neural network. Okay, there's values A, B, and C. You have weights, which are numbers here, and you have this function, which is literally just like combining them, right? So this essentially represents a matrix multiplication. So don't think about it too hard. Just look at these numbers and see how they interact with one another. You have A, B, and C. You have the weights. You have this number Z, which is some multiplication and addition of those numbers that we have here. Is everyone comfortable with this schema we have? Great. So now that we have a way to do a forward pass, which is what this set us up, right? If we put numbers for A, B, and C, we can do a forward pass to the network because we can calculate Z and give that to the loss function, right? So the loss function, we take our MSE, and in a way that I won't get into it too much, but you basically just take the derivative of that, right? And you'll ultimately end up with this number, and this is what we have to worry about. And I can talk about it more later, but after you run the network forward, you are going to get something backwards, like a backward stream. So it's called the upstream gradient, right? So this is some kind of quantification of how much does this function affect the output, right? So Z is the final output. You check Z versus some Y true value. You compute the derivative, and then you pass it back to the network. And this kind of starts a chain reaction, which will slowly update all the weights, right? So this is the upstream gradient. Is everyone comfortable with that concept, right? It is some notion of how Z influences the loss, right? We good? All right, cool. So let's kind of look at the calculus now. This is the derivative of the loss with respect to Z. I'm going to set it and quantify it as a number so it's easier to understand, right? So that's 5. We want to calculate the derivative of the loss with respect to the weights. That gives us the gradient. And all we have to do is negate this and add it to the weights, and we have updated our network to be a little better, right? Because you can calculate the direction of steepest descent in this landscape, which is already kind of abstract, and then move in that direction. And what it will do is guaranteed it will improve the network, right? Because you're doing calculus. It's pretty deterministic. So actually, I'll wait a little bit before I say this. But so here is let's zoom in on the derivative of loss with respect to the first weight and see how we can calculate that with the information we have. We can apply the chain rule of calculus, which is super important. I wish I paid more attention in high school. So we can take the derivative of loss with respect to the first weight and decompose it into 2 different derivatives. One, which we already have, is 5. We know that number, right? It's quantifiable. And we need to find the second term. If we can find this second term, derivative of Z with respect to the first weight, and multiply it by this, we know how much to adjust the first weight by, because we have the gradient, the step in that direction, the W1 direction. So I want you guys to turn and talk with each other. How do you think we can compute this value right here? We have this one. How do we compute that one? Just turn and talk, and we'll get back together in a minute. Mm-hmm.
I don't have.
What do you guys think?
What were you pointing to? What are
Sorry, you guys are at a weird angle. How do you calculate this one? This term right here.
So how are we gonna find?
So the first weight,
I forget this.
I don't understand the direction of your arrows. Z is the output, right?
Yeah, this is backward pass.
Okay.
Yeah.
So the arrows are supposed to represent
Gradient flow.
Oh, okay.
Yeah. Yeah, it's a little weird, but I should have maybe changed the color of the arrows or something, but they represent gradient flow.
Alright, so we're trying to figure out, saying like how much does Z change
I had to do this in one of my classes.
with respect to
Oh, really?
I actually understand that problem.
Yeah.
And we only it got pretty difficult.
Yeah. It's annoying. It's really annoying. But I think it's useful to understand.
I don't even know how to answer the question. Can we just take that? Can't we just get the derivative of Z?
Yeah, that's the answer.
Oh.
Yeah.
I thought we were gonna need to do more chain rules, but like no, we just.
Yeah. No, that's the answer. Yeah, you got it.
So normally, if you have more layers, you're gonna have a term that's saying like, how did the output change with respect to the first layer?
Just like eraser.
And that was in a
Yeah.
layer.
Hey, what's up?
So what are the equations,
Yeah.
what are the constants?
So
And what are the variables?
I can answer that, but well, technically they're both variables. The A's and B's and C's can change depending on the input to the network, and the weights can change depending on the update rules. But it doesn't matter because if you take the partial derivative, like everything that's not W1 is treated as a constant.
Oh.
Yeah.
Yeah.
Okay.
Yeah.
That's what I was.
Yeah.
I was about to say.
Yeah.
I was a little confused on what was the variable.
I'll step through it. It's a little strange. Sorry. Yeah.
Okay, the output was this equation, and so I can just plug that into
Okay. Awesome. I think some people had an answer, so I would love someone to tell me. Even if you're terribly wrong, it does not matter. So please give it your best shot. Anyone? Your best shot. What do you think? How do we compute partial z over partial weight 1? I wish I had those popsicle sticks that like I could draw someone from random. Yeah. Yeah, but it'll get people talking. So I'm gonna do it. But is there anyone? Like someone just give like their best shot. Like even if you say like I don't really know, but maybe it goes in this direction.
You're going to take the partial derivative with respect to W1. And that's going to make everything else cancel out.
That's the answer. Yeah. You just look at this for now. You literally just take the derivative of z with respect to W1. That's it. And the way partial derivatives work is if you are not this term, you're a constant, basically, right? Which is really useful because then we can ignore this part of the equation and literally just take the derivative of W1 times A with respect to W1. A is a variable in this case because it can change. But what's like derivative of 2x? What's the derivative of 2x? Right. So you can see how that comes out, right? The answer is just A. You get A. Like that is the derivative of z with respect to W1. And for W2 it's B because now this term's important. And for W3, oh my god, I didn't change that. It's C. It's C, guys, please. And then you have it right here. Okay, great. So because that term's important. Oh my god, I typed this so fast. Yeah. So it kind of makes sense how we calculate each of these terms.
Can I just add a little bit more?
Yes, go ahead.
Can you go back one slide? So then, since this neural network is literally just one layer, what that is saying is that the amount that changing A changes this final output is just A, right? So if I increase A by 1, it affects this final output by a factor of 1 because like we're multiplying it by 1, like we increase A by 1. So it's just like it's just saying that that's a linear relationship, right? So if you have more layers, or if you have activation functions, I think you were showing the sigmoid function.
Mm-hmm. Yeah.
So if you have that, then it becomes not a linear relationship, which is good for close linear.
Yeah. It's still possible though, is the point. Like you just take the derivatives. It's very much not like magic is the point of trying to get across. You could do it by hand, but I would don't do that. Oh, sorry. Yes.
Could you
you re-explain what the flag is representing?
Oh yeah, for sure. Now maybe it'll be better in context. So essentially what happens is we do a forward pass to the network. We give values for A, B, and C. We compute Z like this. Okay, it's just algebra so far. And we plug that into a loss function. We have a ground truth label, what we wanted Z to be, right? So that is a function. True label minus like guess label, right? And if you take the derivative of that, it's just is there a map anywhere? It's fine. So tell me if you can see this. If we have like let's call this Z true, right? Minus Z hat, or predicted Z. Remember, all we have to do is just take the difference of the two and square it. We can take the derivative of this function as well with respect to this term, which is that. And we just literally just get so now what we do is we have these numbers. We have this. We have this. We have a derivative. We plug those numbers in, and we get the upstream gradient. Right? So it's like basically what we did here, like one step forward, right? That's the derivative with respect to the loss of the final layer here. Does that make sense? Anyone have any questions regarding that?
If the derivative of like Z at W1 is already A, why would you need to calculate the like Z derivative at W1 again? Like this A exists.
Yeah. So this is like a incredibly simple neural network, right? But the concepts can be applied for a larger one, like the one we saw. In that case, there will be a little more complex of a relationship between the variables, but you can still take the derivatives and calculate which step to move. In this case, yeah, it happens to just be A. Well, that's what we expected for the reason Chaitin said, right? It's a linear relationship between them. But if you add a nonlinear activation function, which is what gives these neural networks power, it's not so easy. Right? So we have that, and now, we just calculate the downstream gradients for these guys, right? So this was 5. We knew that the derivative with respect to Z was A. You multiply those two together like the chain rule, like literally we have calculated this and we have calculated this and we are multiplying them together. And now we have the downstream gradients for these, like how much do we want to, we can change the weights here, but then now we can make the gradients flow back one more step. And so on and so forth. And as it goes backwards to the network, you update the weights. Relationships get more and more complex, but still just calculus. And at the end of the day, it's lost dot backward. So, yeah. So the PyTorch has something pretty cool called like AutoDiff and like a computational graph that takes care of all this for you. Although you can write your own layers. It's pretty cool. But does this make sense how we can essentially take this framework we talked about and just apply it iteratively backwards? Just like how we applied the process for forward propagation iteratively forwards. Right? Does it make sense how it goes forward and back?
When will you calculate update the weight?
Sorry?
When will you update the weight?
Once you've like calculated all of them and like how the relationships exist, then you basically have for each weight, what do you want to be changed by? Just subtract them, right?
And then go to forward and backward again.
And yeah, exactly. And repeat the process. And each time you do that, the network gets a little more accurate. That's kind of going down that loss landscape that I talked about, right? So we are adjusting where we are on that landscape by changing the weights. And we're doing it in such a way that takes us lower and lower by each step. And by the time it converges, I erased that. By the time it converges, not actually converges, but it gets stable, we can say we have a trained neural network that can classify dogs and cats. So, what time is it? Oh, bro. I will go over this really quickly. Remember how we talked about, someone asked a question about local and global minima? So essentially, like, there is a little more nuance to it than just like we will always get the right answer, because here is what we calculate. If you just subtract like that from the weights, like take the full step, you tend to like actually bounce around, like you overstep, like you will literally like, you know which direction you have to go, but you like jump in that direction, right? And you might jump over the pit you're trying to get into, and then you try and jump back and forth, and you'll never get to the pit, right? That's what a high learning rate does. That's bad, right? If you have a low learning rate, you'll take little eensy bitty like steps towards the bottom, and sure, you'll get there, but you'll get there like way too slow. So you have to find a good balance of like what proportion do we want to consider this gradient in, so that we can go quickly down to the bottom. Like, see, much too high. Technically, even though we have like, and this is why like sometimes the performance can actually degrade if your learning rate isn't tuned properly, because essentially like, you know what direction to go, but you take way too far of a step, and then way too far of a step, and you can never get back. You will just bounce all over the place and just make the network worse. That's why you can't have too high of learning rate. Okay, we're almost done. So now that we've done all that, first, are there any questions?
In the last slide, what does
Lambda is the learning rate.
okay.
Or it's usually like 0.01 or something like that. Yeah. Anything else? Yes.
Is this something you choose, or how is the
Yes, that is called a hyperparameter. It's something you choose about the network's design. Remember when I said deep learning is somewhat of an empirical science? These are the empirical choices that you have to make. In different, yeah.
Would it be possible to choose a high learning rate initially and slow down the rate?
That is learning rate scheduling. Wonderful. Yes, there's tons of tricks like that to start off like that. And then there's like cosine warm-up schedulers, because sometimes you don't want to start off too fast. And there's a lot of ways to like modify it. And those are in CSE 493 G1 or 599 G1. I don't know. It's one of the courses. It's deep learning. Ranjay Krishna, Ali Farhadi teach it. And it's a wonderful course, but it's hard. It kicked my ass, that's for sure. But now I can talk about this stuff. Anything else? Sorry.
How do you guarantee that you find the absolute minimum instead of the local minimum?
You can't. You legitimately cannot. So you don't know. Like that's the thing I'm going to get into here. Machine learning, you know you're at the best place you can possibly be, but that best place might not be the best, like good enough, right? But you know, like for a fact, it's the best place you're going to get with that method. Deep learning. Oh, sorry.
Well, you can. He's right, totally right. No guarantees, but you can randomize in a lot of different places. So just keep running it with different random initials, tricks like that to try to get, better coverage of this kind of map that we have.
Yep, totally. So it's not like hopeless, but it's more difficult for sure. So it's like you trade off, like you have the power of a deep learning, like the neural networks, but you don't really know if it's going to be the best solution, right? That's the trade-off. So here, machine learning, theoretical guarantees with a global minima, meaning it's the lowest point on the loss landscape you can possibly achieve. Closed form solutions are possible, and you can do it without too intensive computing, although inverting a matrix is bad, or not bad, it's very difficult. So usually even then you do iterative updates. But anyway, the closed form solutions are possible, which I think are really beautiful and cool. So look into ridge regression's closed form solution if you want. It's really interesting. And you have powerful models with gradient boosting trees, so XGBoost, LGBM. Those are packages that you can use in Python to get like really, really powerful models. It's like machine learning, right? It's not technically deep learning, but there's still like the most modern methods are still very good. It's not like deep learning beats everything, right? And there's a lot of strong science behind the model design. So you kind of like, if you really, really, really want to be the best at that, like certain task, you can like look and read a lot of papers and figure out how to do something really well. For deep learning, non-linearities make the loss landscape no longer convex into like a bowl, but it turns it into just like, I don't know, like crazy, just up and down, right? So there's no guaranteed global minima. Usually requires a GPU, really powerful models and performance transformers, and model design decisions can seem arbitrary. you have to pick hyperparameters like learning rate. You have to pick how many layers in your model. You have to pick how many nodes per layer. A lot of things. Do you want to do like warm-up scheduling? There's like other ways to update the weights that require even more parameters, but they're stronger. Like there's so many decisions you have to make, and you really don't know how they're going to affect your final result until you try it. And trying it requires a lot of compute. That's the problem. So last question. What should I use to cut my sandwich in half? This is related to the course, I promise. Just tell me what I should use to cut my sandwich in half. Somebody? Y'all? Yeah. Someone. What should I use? The bomb? Oh, bro. Okay. Yeah. Look at this.
I feel like it's the knife, but it could be a tricky question.
Yeah. Hardest question I asked all today. Yes. So like the idea is this is a simple thing. It's a sandwich I made. So I can cut it in half with a knife. Here is the parallels. That's your data. The knife is machine learning, accurate, precise, but it doesn't have the destructive capability. It doesn't have the power of a bomb, right? Like, if someone's like, if you bring a knife to like a fight and the other dude's got like a bomb, like you're screwed. Like you can't do anything about that, right? So it's more powerful, but sometimes you don't need to nuke your sandwich. That's the big takeaway. You don't have to nuke your sandwich, guys. Okay. All right. Are there any questions?
You said we choose like how many, like we choose a lot of things. I feel like from what I understood, I don't get what's hidden. Like what part of it is actually hidden?
Like the network. Well, when it says hidden, it just means it's sandwiched in between the input and output layers. We can see them. We can mess with them.
Okay.
Yeah. So it's not actually hidden from you. You choose them. That's just a name given to them.
Okay. So what's the unknown part? Like what don't we understand?
So these weights are not by themselves incredibly interpretable. Like you could look at all the weights for a trained model, but all you'll see is just a bunch of numbers. That means something to the model, but not to us. There's a whole line of work trying to solve that problem. You basically, how do we interpret the weights? One of the ways is saliency maps. If someone wants to come up to me and talk about that after, it's a super cool concept. But there's a lot of ways to like try and understand what the model is doing, but it's hard because it's literally just numbers. Like it knows what it's doing, but we don't. Anything else?
How do you know when to respect the person?
So I think image recognition is a pretty nice one, like that deep learning, you can throw at it, and we'll have a computer vision unit later. It tends to be like, usually actually, if it's like tabular data, as in like just numbers, housing prices, so on and so forth, it's good to start with like machine learning. Mainly because you might not need that much power to do like the separation, and you can show that you've done the best you can, right? And also it's like kind of hard to like fit it. Not hard, it's just like, it's like unnecessary to fit like a deep learning model to calculate housing prices in California. It's really not. But like a use case of deep learning would be like, cancer cell recognition within like some kind of images. Like that's complicated. What is the space of that? You don't really know. But if you have defined features, you can use machine learning. Remember I said deep learning learns the features for you? If you have features, you don't really need to use deep learning. All right. Yes?
How do you actually go about choosing the network structure and the parameters that you said can seem kind of arbitrary?
Yeah, okay, so I would just say, you pick them yourself. There is some science to it, although it's very loose, like how do we pick these things? Generally, you don't want to make like, I don't know, huge jumps in size. I think that's do you have any like empirical decisions that are generally good for neural networks?
For hyperparameters?
Yeah.
There's hyperparameter tuning, so there's lots of different techniques. You'll do it in deep learning if you take that. Honestly, there's like rules of thumb, and then basically you set up like a grid search around with that rule of thumb at the center, right? Or you can do Bayesian optimization, which is just like, okay, well, if I try this one and it worked really poorly, I don't want to try a lot of stuff right around that one again, stuff like that. But you're just searching. Also, we should do questions. Like, you guys should come up to us and ask them, and everybody can make solutions.
Okay. Yeah. Sorry, guys. Okay. Wonderful. We're done, right?
Yeah, thanks for staying over. Thanks for Discord for updates.